today we're going to talk about relative velocity. Relative velocity is going to be talking about velocity from different points of view, or we call it different frames of reference in physics. So what I used to think about is at the airport, if you get on the people mover and you're on that escalator and it's moving, or the people mover that's moving it this way, and someone else is taking the people mover in this way, as you pass, it almost seems like that other person's going really, really fast. The other situation is that if you have two people that are moving along the people mover simultaneously next to each other at the same place, it looks like that other person's not moving at all with respect to you. So what we're going to be talking about is relative velocity. So it's going to be the motion of one object with respect to another object. So another example would be, I always think of I'll be stopped at a red light and the car next to me will start moving forward, and I'll look over and it'll feel like my car is moving backwards. But in fact, the car next to me is moving forward. It gives me the feeling that I'm moving backwards. So my car, with respect to the car next to me, is actually moving in a negative velocity. The car next to me, with respect to my car, is moving in a positive velocity. Now, to someone on the side of the road, my car has a zero velocity and the other car has a positive velocity. So you can see that the velocity changes when you look at it in different frames of references, or relativity, or also with respect to different positions. So here's an example. If I'm driving down the road at 40 miles per hour and I'm going this way, this is my velocity relative to the street. So if there's someone standing on the side of the street, they see my car moving forward and I can be clocked at 40 miles per hour. Well, as I'm driving down the road, another car is going to pass me. They're going 30 miles per hour in the other direction. So velocity 2 is relative also to the street. Well, what does it look like is going on if I'm in my car? So my car, this car relative to my car, is actually going to look like they're going 70 miles per hour, very, very fast past it, where you'd add them together. Now, if we wanted to talk about the velocity of the street relative to car 1, you would take the subtraction of the two. So you have 40 miles per hour minus 30, and you'd end up with a 10 mile per hour going that way. Okay, so we're going to keep going here with this relative velocity. V1 is u relative to the street. The way that we reference this is u with respect to the street. So we have u, we'll use a slash with respect to, and then it would be the frame of reference or the object that it's viewed at. Velocity 2 is the other car relative to the street. So this will be the street relative to the other car. And then if we add them together, it's u relative to the other car, and so it'll be vy slash o, the other car. Okay, and you don't really need to worry about these different terminologies. The key here is that when we subtract the two, v1 minus v2 is going to equal v3. So we have velocity of u with respect to the street minus the velocity of the other car with respect to the street is going to equal velocity of u with respect to the other car. So if we keep the same pattern here and we just use general terms of A and B, so this is going to be velocity of object A with respect to B minus velocity of B with respect to C. And for us to find out what velocity of A, object A with respect to object C is, all you have to do is subtract the two. So this becomes our general equation. So what we're really doing here is we're subtracting vectors. So in that previous example, both vectors were in horizontal direction or on the x-axis, so it was easy for us to subtract them. So let's look at an actual problem. Okay, we have a spy. He runs from the front of an aircraft carrier to the back at a velocity of 3.5 meters per second. If the aircraft carrier is moving forward at 18.0 meters per second, how fast does the spy appear to be running when viewed by an observer on a nearby stationary submarine? So here we have, this is our aircraft carrier. We have the spy. The velocity of the spy is that way. The boat is moving this way. And this is the submarine. You got someone else looking at this guy, and we want to find out what is the velocity of this spy relative to this guy here on the submarine. So we're given the velocity of the spy with respect to the boat, and that's how fast he's going, as if the boat weren't even moving, and he's going 3.5 meters per second. We also know the boat is moving with respect to the sub over here at 18 meters per second. The unknown is what is the velocity of the spy relative to the submarine. So what we're going to do is we're going to subtract the velocity of the spy with respect to the boat or the submarine minus velocity of the boat with respect to the submarine. Let me rephrase this back. The velocity of the spy with respect to this boat minus the velocity of this boat with respect to the submarine is going to equal the velocity of that spy with respect to the submarine. So velocity of the spy with respect to the boat is 3.5 meters per second. That's how fast he's running. The velocity of the boat with respect to the sub is 18, and all we have to do is subtract the two, and we have 14.5 meters per second. So this guy right here, standing on this submarine that's not moving, is going to look at that spy as if he's running 14.5 meters per second. In actuality, he's only putting in 3.5 meters per second, but the boat is moving 18, so he ends up, it seems like he's moving much faster. Okay, so now what happens if we're in two-dimensional motion? So the boat and the spy were both on the x-axis, but what happens now if we have something that's in the x and the y direction? Okay, so we're going to use the same method, but our situation is when we subtract vectors, we have to be a little bit careful. Because if I have vector A is going straight up, and I have vector B now that's going at an angle, it's no longer going only in the same direction as vector A. When I subtract them, we think of it as the same as adding a negative. So I can say that A minus B is the same as A plus a negative B. So what we really have to do is we're going to stick with vector A, is right here, and then we're going to add a negative of vector B. Well, the way we make vector B negative is we just flip the direction around. The negative is telling us the direction. So I'm taking vector V and I'm going to flip it around, and that's what I get right here. So now if I'm going to add these two, the way that we add vectors is tip to tail. So I'm going to start with vector A right here. I have vector A. Now I'm going to go vector B right here. And then my difference is going to be right here. So this vector is A minus B, is right there. Okay, so now I can find out what is the direction and the magnitude of that vector. So we're going to get into more specific problems. All I want you to see here is that when we subtract vectors, we really add and then we flip the direction of the other vector, and then we can use our tip to tail method. Okay, so here's an example with this. I have a boat that's heading north. It crosses a wide river with a velocity of 10 kilometers per hour relative to the water. The river has a uniform velocity of 5 kilometers per hour due east. Determine the velocity of the boat relative to an observer on the shore. Okay, so here's my picture here. I have this boat that's crossing the river. The river is flowing this way. It says here the river with a velocity of 10 kilometers per hour. The river has a uniform velocity of 5 kilometers east. So this is the velocity of the water with respect to the shore. This is the guy on the shore, so the water's moving this way. Now the boat is heading north, so it's heading in this direction, crosses the river at 10 kilometers relative to the water. So now what we have to do is determine the velocity of the boat relative to this guy here on the shore. Well, we know the velocity of the boat with respect to the water is 10 kilometers per hour. We know the velocity of the water with respect to the shore is 5 kilometers. So now what we have to do is we're going to find the other one. Okay, so I know that the velocity of the boat with respect to the water minus the velocity of the water with respect to the shore is going to equal the velocity of the boat with respect to the shore, and that's what we're looking for. What is the velocity of the boat relative to an observer on the shore? So this is what we're looking for. Well, our problem is that they're in different directions, so we can't just add these. I can't just say 10 minus 5. Now what I'm going to do is I'm going to create my velocity of the boat with respect to the water plus a negative velocity of the water with respect to the shore. Okay, velocity of the boat with respect to the water is straight up here. Okay, now I'm going to do a negative one of these. So this is velocity of the boat with respect to the water. This, the negative of going this way, is going this way. So now I'm going to say this is the velocity of the water with respect to the shore. And then, oops, and I made a mistake here. Let me just go back because we're doing tip to tail, so it's going to be up here. Okay, so we have velocity of the boat with respect to the water. I'm just going to go back, I apologize for that. Then we're going to do tip to tail here, and this is the velocity of the water with respect to the shore. And then our resultant is what we're looking for, and that's right here. Then this is the velocity of the boat with respect to the shore. So how do we find that out? Well, if you can see here, we have a nice right triangle. If I rewrite this here, and this is my triangle, velocity of the water with respect to the shore is 5. Velocity of the boat with respect to the water is 10. So I can find this using my Pythagorean theorem. And I have 5 squared plus 10 squared. Take the square root of it, and I end up with 11.18 meters per second. And that is the velocity of the boat relative to the observer on the shore. So this guy on the shore looks like the boat is going this way, but in all actuality, it's crossing perfectly straight. But it has to veer that way because the water is going to push it that way. Now, when we talk about velocity, it is a vector. It needs a magnitude, which we just got. And we also need the direction. So we're going to be looking for this theta right here. Okay? So to do that, we're going to do inverse tan. So the theta is going to be the inverse tan of the opposite, water with respect to the shore, over the adjacent, which is boat with respect to the water. And so you can plug that right in, and you can find out what the angle is as well. Okay, so that's enough for the relative velocity. Don't forget to do the assignment on Edline tonight, and then tomorrow we'll do some problems in class. See you tomorrow.